I have already written the limitations as given in NCERT. So now let me explain one by one. So here is the Ohm's law, right? Where V is the potential difference, I is the current, and R is the resistance. Now you see, so according to Ohm's law, so this VI graph for metal should be straight. Here you see, for a good conductor, this is the VI graph. Okay, it's supposed to be a straight line, but here you see it obeys the Ohm's law up to a certain point. Then after that, it doesn't obey that Ohm's law, right? This is one of the limitation of Ohm's law, and this is the VI graph for conductor, good conductor. So similarly, you know, next point is here you see, this is the VI graph for a diode, right? So here you see in this direction, in positive direction, right, in positive direction, for a, suppose for a particular voltage, suppose at 2V, so this is the current you have got, right? But when you change the polarity, so this is a conductor, suppose now this is positive and this is negative. Okay, when the voltage is 2 volt, then you have got a certain current, that is suppose I1 when the voltage is V. So again, if you reverse the polarity, if you reverse it, if you make it negative, it is positive, suppose now. So if you reverse the voltage, then same voltage. So in this case, here you see, so when you reverse this polarity, now here it is, suppose voltage is 2 volt. Now again in opposite direction, now it is also 2 volt, but here negative sign represents that we have altered the polarity. That's it. So here you see, you are not getting the same magnitude of current. Here we're gonna get, suppose, negative I2, right? So negative sign, it doesn't mean that current is vector. Okay, just to represent the direction of current, that's why I have given the negative sign. Let me tell you one more thing. Though the current has a direction, electric current has a direction, but it is not vector quantity, because you see, suppose you have a conductor, this one, and I1 current is flowing through it, and another conductor, this one, that is I2 current is flowing through it, and they are connected at a junction at this point, right? And now in this conductor, the current will be I1 plus I2, and it doesn't obey the vector addition law. Okay, just it obeys the it obeys simply the algebraic sum, right? If you take the algebraic sum, then only you will get the total current. So that's why it is not a vector quantity. So let me explain it again. Now you see, suppose you have a conductor here, 1 ampere current is flowing, and this is another conductor, 2 ampere current is flowing, and this is the junction of these two conductor. Then suppose we have joined another conductor, then current in this conductor will be 1 plus 2, that is equal to 3 ampere. Okay, so here we don't need to take the vector addition, like here 1 ampere plus 2 ampere, then plus 2 into 1 and 2 cos theta. We don't need this angle between these two, right? So hope you have understood this. That is why this current is not a vector quantity, right? So hope you have understood this. So this is one limitations I have explained here. So here you see 2 volt, again here also 2 volt, but now we have changed the polarity, that's why we are writing here negative. And here you see, let me show you again, just wait. Here the magnitude of current is I1, but here we are not getting the same magnitude, right? So similarly, for a material like gallium arsenide, so here you see, for different values of V, we are getting the same current, right? We are getting the same current, right? Relation between VI is not unique. And you see the materials or circuit elements which strictly obey the Ohm's law are known as ohmic materials or ohmic circuit elements. Okay, for example, metals. And the materials or circuit elements which do not obey the Ohm's law are known as non-ohmic material or non-ohmic circuit elements. Okay, like semiconductor, diode, transistor, etc. Right. So hope you have understood this. Now let us discuss about uh, the temperature dependence of resistivity. The temperature dependence of resistivities for a particular material. You see, rho naught is the resistivity at temperature T naught, and its resistivity changes to, suppose, rho when the temperature is T. Okay, when the absolute temperature is T. Okay, then the relation between this rho and T is given by, okay, then the resistivity of at temperature T is given by rho is equal to given by this relation, right? So hope you can you understood this by given by this relation. Now you see, just give me a second. Okay, here you see this alpha is the temperature coefficient of resistivity, and its dimension is temperature inverse. That means we used to write the symbol K for temperature dimensional formula, that is K inverse, right? Now you see, I have shown here the resistivity and temperature graph for copper, nickel, and semiconductor, different materials, right? So this is the graph for resistivity, which is in ohm meter, and temperature in Kelvin. This is the graph for copper, and this is the graph for nickel, and this is the graph for semiconductor, right? So hope you have understood this, and hope you like this lecture. And if you like the lecture, then please do hit the thumbs up button, and also share with your friends and support me to grow my channel.